Okay, we've got something interesting and different today. I want to derive the Fourier series for e to the x from minus pi to pi. We have here all the formulas on the board. I'd like to say that I derived these in a previous video, but I haven't done that video yet, so we'll have to work on that. But you can actually find this a lot of places. If you need some help, I can get you a link or something if you want to see where this comes from, or hopefully we'll have a video for this pretty soon. Okay, so to get started with it, how it's going to work is we want, for e to the x, that's going to be this f of x right here, and our expression is going to be all this stuff right here. The first step really is to find these coefficients, a naught, a sub n, b sub n, and then hopefully get some simplification later on. And so to get all those constants, what we'll do is they're all going to be in terms of integrals. So we just need to kind of plug in over here where our f of x value is just going to be e to the x. This big L value we see all over the place, that's going to come from this. So we're going to say L is going to be just equal to pi. So let's start with a naught right here. So for a naught, this is going to be plugging in for all the L stuff. Sometimes you'll see these formulas already written in terms of pi, because that's probably one of the most common. You'll see it 0 to 2 pi or minus pi to pi a lot. I mean, you can do other things, of course, but here we have minus pi to pi. So we're going, that's the way our integral is going to look. Plug in our f of x, and we've got a very simple integral to do. So we'll integrate this. We've got our 1 over pi. This is just going to be e to the x evaluated from minus pi to pi. And so our a naught is just going to be e pi minus e minus pi over pi, and that's going to be what we're going to plug in right there. Okay, next we're on to our formula for a sub n here, just plugging in all the pi's all over the place. The first thing we can do is in here we can just cancel the pi's. Again, that's why a lot of times you'll see this formula, if they already have a pi in it, then this is already canceled out and you just have cosine nx. Now for this one, we've got a little more work because we've got to do integration by parts, and I don't really have a lot of room for the DI table, but we'll do it really quick. This is kind of your common setup. So we have cosine nx, I'll differentiate that, and I'll integrate e to the x. When we differentiate here, this is going to be minus n sine nx. Integrating this to e to the x, of course we'll do it again, and we'll get another e to the x. Here, we'll do this again, differentiating one more time. This is going to become n squared cosine nx. And that's a mistake, I actually lost the minus sign, so let's put that back. So we'll have part of our answer on the diagonal. Now the thing to notice about this last row, this is going to be an integral, but when we integrate it, think about like minus n squared is a constant. Put this back in, and what we have here is going to be part of our original expression. So actually, if you go back to this and you multiply by pi on both sides, then this integral is going to be equal to pi a n. So I can call this right here pi a sub n. So let me see if I can squeeze this in over here. So we're going to have, we've got the 1 pi out front. Then I'll factor out an e to the x out of both these. And then what's left is going to be minus times minus here is plus. So we're going to have cosine nx plus n sine nx. Here, let me kind of move this so I can kind of try to squeeze this in, because I'm really kind of boxed in right here. And then for this last part, the way I'm going to write it is I'm going to have it as minus n squared pi a sub n. But I do need to distribute this 1 over pi into this as well. So we're going to have this pi here, what's going to just cancel with that. And let me just move this out of the way so we can solve for this thing. Now for this first part, we need to evaluate it from minus pi to pi. When we do that, this is all going to be equal to a sub n. We're going to have 1 over pi. Plug in pi, we have e pi cosine n pi. Let's just leave that for now. Cosine n pi plus n sine n pi. And then let's kind of bracket it. Then the next part, minus. Plug in minus pi, this is going to be e minus pi. Cosine, when you plug a minus pi in here, cosine's an even function, so the minus sign doesn't matter. So we can just write this as n pi. And then over here we have plus n sine minus n pi, but sine is an odd function, so let's bring the minus over here. Now keep in mind, going back to what we're doing, n is going to be an integer value because it's going to be part of this sum here. So if n's an integer, sign for an integer multiple of pi, that's just going to be 0. So this term's going away and this term's going away. For cosine n pi, that's going to be going between, for integer values of n, it's going to be -1 plus 1, -1 plus 1. And it's going to be, so for all the odd values of n, it's going to be -1. For all the even values, +1. So we can actually represent this as -1 to the n for this and kind of get rid of that and factor it out. Next, let's just keep in mind we've got this minus n squared an over here. What I can do is bring that on the left side of the equation, add it with this, factor out a sub n, and what we're going to have here is going to be 1 plus n squared a sub n. So on the right side, if I simplify this and I factor this -1 to the nth out, I can have this as -1 to the n. We still have a pi in front, and then everything, all that's left is just going to be e pi minus e minus pi. But I want to solve this for a sub n. All I'm going to do is divide by 1 over n squared on both sides. Don't worry about this, that's kind of a mess, but we'll just divide it over here. So I need to divide this by 1 plus n squared. And that's going to isolate our value for a sub n. Okay, for the last constant, we need to find b sub n. Really similar to the last one, the only difference is sign. I plugged in the pi there and simplified this, so we already have this down to nx. Same kind of thing here, we want to do integration by parts. I'll do the di method again, and we'll do it kind of quick because it's really the same deal almost. So we integrate this to e to the x. This is going to be differentiate sine nx. We get n cosine nx. And then here we get minus n squared sine nx. Again, we've got our solution, or part of it, on the diagonals. Let's come down here, I think. So we've got our 1 over pi. Let's factor the e to the x out front, and we're going to have sine nx minus n cosine x. The same thing we saw before is going to happen here, where we found in the other one it was a sub n. This is going to be basically our b sub n. We could put the pi, but it's just going to cancel. So what I can do is write this as minus n squared b sub n. And so why don't we just do this all together? Let's add this on the other side. So if I add n squared bn here, over here we're going to have 1 plus n squared on this. So I'll get rid of this, and we'll just evaluate this thing from minus pi to pi. Plug in pi, what's going to happen? We've got 1 over pi, e pi. Sine n pi, that's going to be just a 0. So let's just deal with that now. Same as before. Minus n. Cosine n pi, we found that to be -1 to the n in the previous example. Then plugging in minus pi, this here becomes, here, let's make it clear that we're going to distribute in that piece. So this becomes e minus pi. Again, minus pi doesn't matter. That's still sine minus pi. It's going to be a 0. So that's going away. Minus n cosine n minus pi. It's an even function. Cosine minus n pi is the same thing as cosine n pi. So this is going to be -1 to the n again. So let's see if I can put this all together. This we have in common. We can factor it out here with this pi. Then we have a pi. Okay, so we got the pi in the denominator. We're gonna pull out this e pi minus e minus pi. So let's kind of do this part. Then we actually have this minus n in common here. It's a little confusing with the 0. Let's get rid of that. So we're just multiplying this here. Now, if we multiply this together, we would actually reverse the sign. I don't want to do it. I kind of like having, because this is the same way as we have it here. So I'm going to factor minus n out here. Sorry for the close call here. And then all we have to do is, again, isolate our b sub n, same way we did before. Just divide by 1 plus n squared, divide by 1 plus n squared, and that's our value for b sub n. And now finally, after all that, we've got our constants. I always find this part kind of tedious. It takes quite a bit to get to the point where we can actually calculate our series. So now we just can kind of plug in our f of x value again. We're finding this is going to be our expression for e to the x. Now before I plug everything, I do want to try to save one step. We have a constant term in common in everything. Basically this here, this whole thing, we have everywhere. The exact same thing in each of our constants. So it's going to be in each sum. We can just pull it all the way out front. So doing that, we'll have e pi minus pi over pi in front. Then for our a naught term, when you factor out everything, it's just going to be a 1 left over. So this first piece is going to be 1/2. Then for this sum here, what's going to happen, we have what's left of this times cosine, where L is going to be pi. So this is going to end up being, let's see, minus 1 to the n over 1 plus n squared. And then when we cancel this out, we're going to do the same thing over here. This is just going to be cosine nx. And then really similar for this other one, here we have this minus sign. Let's use the minus sign to bring it out front of the sum. So then what's going to happen, I'll have this as n minus 1 to the n. We're going to have this, we still have the 1 plus n squared. And then I'm out of space, but this right here is going to be this sine nx term. And then let's just see what kind of simplification we can get on this. Let's actually combine these sums together. So we'll leave the first part as it is. And then bringing this into one sum, what's going to happen, we can put it all over 1 plus n squared. And then we can factor the minus 1 to the n out front like this. And then what's left is just going to be cosine nx minus n sine nx. And that's going to be our Fourier series for e to the x. But I do have an alternative motive here, because what I want to do is I want to use this to derive a couple of nice values. So I was thinking, what are the nice values to plug in for e to the x? Well, the first thing that comes to mind is 0. If we plug a 0 in there, then on the left side we just have a 1. We can go ahead and we can reduce everything. In the sum, when you plug in a 0 on the cosine, that's just going to become a 1. So we have minus 1 to the n. This is just 1. And then you plug a 0 in here, the sine term goes away. So that's going to cancel all that out. And really we just end up with minus 1 to the n over 1 plus n squared. But then what you'll notice is this sum is basically something we did recently. I did the sum of 1 over n squared plus 1, but I've also done this one, minus 1 to the n over 1 plus n squared. So with this, what this is going to allow us to do, everything else is constant, so we can actually solve for just this right here. I can call this thing s, multiply on both sides. If I multiply in on here, to get rid of this, just multiply by the reciprocal. So then that's going to cancel off here, and then we'll just get it on the left side. And then to isolate our sum, all I need to do is just subtract a half on both sides. And so let's see what we have. For the sum from 1 to infinity minus 1 to the n of n squared plus 1, we get just pi over e pi minus e minus pi minus 1/2, and that's it. Alternatively, we could write it as pi over 2 hyperbolic cosecant of pi minus 1/2. So that's kind of another way to write it. Okay, so there you go, Fourier series, e to the x. Thanks everyone for watching. Have a good day.